Okay, but now we start with Dan Voiculescu from Berkeley, and he will talk about Macaev, operator norm, entropy, and supramenability.
So I'd like to start by thanking the organizers for the opportunity to be here at this conference and to give a talk. Very nice. So you see the title of my talk is Macaev, operator norm, entropy, and supramenability. So entropy appears in many ways in connections with operators. I will talk about a situation when entropy appears connected to operators, which is which is less known, which is not so well known as the many other ones. It is about entropy appearing in connection with perturbations of operators, and it is about a certain approach to certain perturbation theory questions which I developed, and which relies on a certain number invariant ki of tau. Tau is an n-tuple of operators. I is a normed ideal, and there is a certain number which corresponds to that. It appears in many questions in operator theory. And the ideal which connects with entropy will be the Macaev ideal, about which I'll explain more. It's also known as Lorentz infinity, 1 norm. This is my support. So there is a certain number with k iota of tau, which it measures, technically speaking, the obstruction to quasi-central approximate units relative to a certain, to the normed ideal I and the n-tuple of operators tau. And the emphasis in this talk will be on the ideal being this, what I denote C minus infinity, or if you want, it's on the Lorentz scale with two indices, the infinity, 1. Is a Macaev ideal where there are connections with entropy, and recently connections with supramenability of groups has appeared. I will also very, very briefly hint at the end about a new direction the study of operator perturbations with these techniques have taken. It will be only a hint about some new structures, commutants, mod-normed ideals. So here is the notation about normed ideals. So a normed ideal, you know, I think everybody is familiar with Schatten von Neumann P classes, of which P equal 1 is the trace class, P equal 2 is the Hilbert-Schmidt operators. So there is an ideal I of compact operators among all operators. The Hilbert space will be separable infinite dimensional. And that's the norm. And I will be especially interested in these things I denote by C minus P, and which other people may prefer to denote by C P, 1. That's the Lorentz PQ notation, the double indexed spaces. So it's CP, 1 or C minus P. And if you take P to infinity, then you see the norm which would have been for the P class, for the Schatten class, it's a small LP norm of the eigenvalues of the absolute value of the operator, the S numbers. For the T minus P is this thing the Sj, j power minus 1 plus 1 over p. Now, if you make p infinity, the 1 over p disappears, it's 0. And you have this Sj, j minus 1, and that's the Macaev norm. This terminology with Macaev norm is because I learned my operator ideals from the Gochberg-Crane book, one of the earliest great books about this subject, and where it was called the Macaev ideal. And here is the definition of this number, k iota of tau. So tau is an n-tuple of bounded operators, T1 to Tn. And then k iota of tau is defined in the following way. It is the smallest number C. It may be 0, it may be infinity also, smallest positive number, such that there is a sequence Am of finite rank positive contractions. So the AMs are between 0 and 1, and they are finite rank. And that's this maximum of commutators of the AM, comma Tj, commutator AM with the Tj's, and you take the max over J, so it's T1 up to Tn. So all these commutators in I norm, their max should converge to this constant C. The smallest such number. So if C is 0, it means you have such an increasing sequence of finite rank contraction. They grow to positive contraction. They grow to the identity, which commute better and better. But it is possible that such a sequence does not exist. So there is an obstruction to the existence of such a sequence. And the interesting thing is what creates this obstruction. Why isn't there such a sequence AM converging to 1 in the norm I? Of course, the whole thing depends very much also on what norm you choose. So the ideal I, with respect to which all this is defined, if it is Cp, the Schatten class, it will be denoted, I will denote this k iota of tau with simply kp of tau. If it is this p comma 1 or c minus p, I will denote it by k minus p of tau. And if p is infinity, I will denote it, of course, with k minus infinity of tau. I should tell you from the beginning that if p is equal to 1, then k1 is the same thing as k minus 1, because the Lorentz ideal I1, 1 is the same thing as the Schatten ideal 1. So the trace class and 1, 1 Lorentz are the same. And I should also tell you that if p is larger than 1, then the Schatten classes are not as interesting as C minus p. The C minus p are much better. What are the C minus p? If you look at the norm, you know, if you have a projection on a d-dimensional space, then its Schatten for Neumann norm is d to the power 1 over p. The p comma 1 ideal is the smallest ideal where the norm on the projections, on the finite rank projections, orthogonal projection, is of the same order, is something like a d to the power 1 over p. So it's the smallest such ideal. So if you want, it's the biggest norm of such an ideal, for which on projections it's like the Schatten class, Schatten von Neumann class. So here are the general properties of such a number. When the p varies, and I will look at k minus p of tau. Why am I looking at k minus p of tau and not at the Schatten class, Schatten von Neumann class, which is the usual idea of p class? It's because, so for p equal 1, it's the same thing. But if p is not 1, then kp is only 0 or infinity. If p is different from 1, kp of tau can be only 0 or infinity. So it's not a very interesting number. The k minus p is much more interesting than the kp. So when p varies, this function p goes to k minus p of tau, tau is fixed, is a decreasing function. Yeah? The larger the ideal, the easier the commutation. And when you take p to vary from 0 to infinity, there is a certain point, possibly a p0, where things may change. Up to p0, you'll have that the k minus p of tau is plus infinity, and after p0, it is 0. So it starts with infinity, and it ends with 0. Of course, this is not the case if you choose, if this p0 happens to be 0 or infinity, when things are different, yeah? Then it will be infinity before infinity, and at infinity something may happen. So you have first a big piece where it's plus infinity, then it's 0, and at that point p0, well, there various things can happen. It can be any number between 0 or infinity. Yeah? So there is one point where something is measured about tau, and before that the measure is plus infinity, and after that it's 0. The third property is that if you restrict the ideal I to the closure of the finite rank operators, there are such normed ideals where the finite rank operators are not dense. So if you restrict to the finite rank operators ideal I, then this number k iota of tau is an invariant mod the ideal for the n-tuples. Yeah? So two n-tuples which differ by something in the ideal, which are equivalent modulo of this ideal, the number k iota of tau is the same. It's an invariant with respect to that. So here the connection with perturbation starts appearing. Yeah? It's something which is the same after a perturbation from the ideal. Now, one wants, of course, to evaluate this number k iota of tau. To evaluate such a number, you need upper bounds and you need lower bounds. Upper bounds are clearly how to get because of the definition. Yeah? The definition is that the k iota of tau is the smallest number C such that these commutators, their norms should converge to C. So upper bounds are obtained by using just the definition. But what about lower bounds? Well, lower bounds have to do with traces of commutators. So if I have such an n-tuple, and I will simplify, I will make tau equal tau star, because I'm taking all the time commutators with positive operators, I can always, up to putting some evaluation, some constant 2 times or something like that, it's the same thing as taking the Hermitian and anti-Hermitian parts and changing the n-tuple or adding to the n-tuple the adjoints. So let's assume tau is equal tau star, so the operators in the n-tuple are Hermitian. And then the fact that k iota of tau is positive is equivalent to the existence of operators yj, this yj, Hermitian operators yj, in the dual of the ideal. So if the ideal would have been Cp, it would have been the Cq. If it's C minus P, well, there is something like C plus Q, 1 over P plus 1 over Q equal to 1, such that the trace of the sum of commutators, you have the commutators of the Tj's and the Yj, if you take the sum of these commutators and you multiply by I, then this is an operator which has, for which trace has a meaning. So it is an operator which is a trace class operator plus a positive operator. And the trace of this has to be strictly larger than 0. Yeah? Imagine situations when, it's very delicate here. This is the Tj yj, it is that the Tj commutators with yj Yj is in a bigger ideal, but so this is not something for which there is a trace, but the trace arises when the sum, when you take the sum of all these commutators, you have the trace. And this trace, well, it may be something with an infinite part which is not trace class, but the trace can be computed. So the positivity, if you can arrange commutators like that, such that you get a positive trace, then, for instance, a typical example which you encounter often when you deal with questions in abstract scattering theory or so, is that you take the Hilbert transform and you take the commutator of the Hilbert transform with the position operator. This kind, but you say you do this on a finite interval, not on the whole real line. Then you get such a commutator situation. And for the Macaev dual, for the Macaev ideal, its dual, which should appear here in the commutator sum, is the ideal C plus 1, which is a very well-known ideal and which in the Gochberg-Crane books is also called Macaev ideal. It is an ideal which people in non-commutative geometry like very much. It is where the Dixmier non-normal trace lives. And the norm of this C plus 1 is obtained in the following way. You take here the sum of the first MS numbers and you divide by the beginning of the harmonic series, so something like logarithm of M, and you take the sup over all these. This is the, so it's something which you call usually something like C1 comma infinity on the, something like that on the Lorentz scale. Now, what is this k iota of tau? How should we understand this quantity? It is, if you think of the ideals somehow, they form kind of ordered set for their size, you can say that there is a number or something, the size I, the size of the ideal. So it is chi iota of tau is the size I dimensional measure for the n-tuple tau. Here, dimension p, if you take a number p between 1 and infinity, dimension p will correspond to the ideal C minus p. I explained why Cp is not a good idea, because Cp, this number kp of tau, if p is not 1, is either 0 or infinity. It doesn't measure something precise. It measures only 0 or it's infinity. But if you take C minus p, you can get more interesting things. So let's take tau, an n-tuple of commuting Hermitian operators. Yeah? So this n-tuple has a spectral measure, and this spectral measure, so it's a projection-valued measure, and for each Borel set there is a projection for each Borel set in Rn, and it has, like every good measure, a decomposition into a Lebesgue absolutely continuous part and a Lebesgue singular part. And the Lebesgue absolutely continuous part has a multiplicity function, which is a Lebesgue measurable function on Rn. So this number k minus n of tau, so the ideal is this n comma 1, if you raise it to the power n, is a certain universal constant gamma n, which is neither 0 nor infinity, the integral of the multiplicity function integrated against Lebesgue measure. I don't know these numbers gamma in general, but gamma for n equal 1 is exactly 1 over pi. So you see from this, since this is an invariant when you perturb tau from the ideal C minus n, somehow if tau and tau prime are differ by a C minus n perturbation, then the two multiplicity functions must have the same integral. In particular, if one n-tuple has only singular part, if the spectral measure is Lebesgue singular, then the other one must also be Lebesgue singular because the integral is 0. And you can take this formula and apply it to functional calculus applied to tau, functional calculus with C infinity functions, for instance. And then this formula gets inside also some determinant of a Jacobian. And this then gives you the possibility actually to realize that the multiplicity function is invariant if you make C minus n perturbations. So one consequence of this is that if you have tau and tau prime, two commuting n-tuples of Hermitian operators, such that the difference is in C minus n, then the Lebesgue absolutely continuous parts must be unitarily equivalent. So you restrict to the projecture corresponding to a Borel set, which leaves out the singular part of the Lebesgue measure, of the spectral measure. That's the Lebesgue absolutely continuous part. This, in case n equal 1, this is a corollary of the Kato-Rosenblum theorem of abstract scattering theory, which guarantees the existence of generalized wave operators. And also here, in this context, one can go further. That is, one can, with these techniques involving the numbers k minus n, one can get existence of wave operators of this type. Only the phenomena are different than in the case n equal 1. So it's only the beginning of the story that the Lebesgue absolutely continuous parts are unitarily equivalent. Now, with this technology, one can go also to the case of when the number n is not an integer. That is, one can go over to fractional dimension. And somehow the technical results involved here, because there are things about some singular integrals which play a role here. It's like the role of the Hilbert transform in case n equal 1, which is so visible when you look at perturbation theory of one Hermitian operator. I have a paper, an old paper with Guy David, and one can recover many of the things. Actually, the technique is about as strong, if you want, as for an integer, but the picture is more complicated because in dimension n, somehow there is Lebesgue measure which stands out, while in fractional dimension you have many Hausdorff-like p measures, so to say, and the fractals are more complicated sets. But here is a sample of what one can get. So one of the most important things to prove things for n is to get lower bounds on the number k minus n. This has to do with these commutator sums. And this we could do. So if one has mu compactly supported probability measure, which satisfies this type of condition, that the measure of a ball of radius r is bounded by a constant times r to the p. This is kind of Hausdorff measure. I think this condition may be sometimes called something with Alfors, if I'm not mistaken. Then the n-tuple of multiplication operator by the coordinate functions has this number k minus p of tau m positive. Okay, so this is what happens before infinity. And I promise that at infinity you're going to see something having to do with entropy. Well, at infinity, so the ideal is now the Macaev ideal. There are already a few things which stand out about this Macaev ideal. First of all, this number k minus infinity of tau is always finite. For the other numbers, what happens is that the number k minus p or k iota of tau can be infinity. It can be numbers between 0 and infinity or 0 and infinity. But for k minus infinity, at the Macaev limit, the number is always finite. The second unusual thing is that if you increase the multiplicity of the operator, nothing changes. If you tensor tau with identity on a Hilbert space, the number k minus infinity stays the same. And the third thing is that if you go beyond the Macaev ideal, so if you go to ideals which are larger than C minus infinity, the number ki of tau does not measure anything because it's always 0. So if you go above the Macaev ideal, there are always this kind of quasi-central approximate units, this kind of finite rank operators increasing to 1 and which commute asymptotically in the I norm. So somehow this is clearly something remarkable about the Macaev norm. It is somehow the limit up to which there are interesting things about perturbations in the style of what you know for trace class or so. This number k minus infinity of tau can be non-zero. For instance, if you take the creation operator on the full Fock space, so that's the Boltzmann Fock space, the creation operators S1, Sn. So this is a Kuhn centuple, an extended Kuhn centuple, because the sum of the ranges is not the whole space, it has codimension 1. Then this number k minus infinity of S1 Sn is exactly the logarithm of n. Now, you saw in the properties I listed here, there was the second property that multiplicity does not play a role. And then one might think that, well, there may be nice things to say about k minus infinity of tau tensor tau prime, that this number behaves nicely when you take tensor products. Well, this is not true, because I could find n-tuples tau and tau prime such that this k minus p for tau and for tau prime is 0, and it's 0 not only when p is infinity, but as soon as p is above 1. But if you put them together in a tensor situation, tau tensor 1 and 1 tensor tau prime, the number k minus infinity is positive. This example I found arose from exactly these new connections with supramenability, where there are certain examples of what is called supramenable metric spaces, examples of something like that, an example of Laurent Bartholdi, which inspired this. And now, where does this connect with entropy? There are connections with entropy between these numbers k minus infinity. One thing is that with k minus infinity, one can recover the Kolmogorov-Sinai entropy. So or dynamical entropy. So if I have theta, a measure-preserving ergodic homomorphism of probability measure space, I denote by u theta the induced unitary operator in L2 from this transformation, and by capital phi the multiplication operators in L2 by measurable functions with finite range. So I'm taking kind of all possible finite partitions of the space omega, and functions which are constant on the sets of the partition. And then what I do is I take k minus infinity of some finite set phi of such multiplication operators from the partition and the unitary u, the induced unitary. And I take the supremum over all choices of such a lowercase phi. So I take bunches of multiplication operators by functions which take a finite number of values, and together with u theta, I take the k minus infinity, and then I let the number of such multiplication operators increase. And I define this number hp of theta, which one could call perturbation entropy, something like that. And what happens is that this number hp of theta is equivalent to the Kolmogorov-Sinai entropy. The constants are something like, I think, 1/2 and 6, or probably maybe better, but I know something with 1/2 and 6. And in the case when theta is a Bernoulli shift, then actually one can prove that they are proportional. There is a proportionality constant, and this number HP of theta is exactly proportional to the Sinai, Kolmogorov-Sinai entropy, the KS entropy. There is a problem here, is that this type of induced unitary operator U theta can be defined also more generally. I don't need that the measure be invariant. One can define this number U theta also when the measure is non-singular with respect to theta. Unfortunately, I really don't know whether it is possible to find an example of a situation when the measure is not equivalent to an invariant measure, and when this number HP of theta is finite, is not zero or not infinity. Seems to be a hard problem, but there is room in this definition to go beyond invariant measures. That is, one adjusts the induced unitary with the square root of a Radon-Nikodym derivative and still a unitary. Another situation where there is a connection is with the Avez entropy of random walks on groups. So I have a group G with generator G1, Gn, and mu is a finitary probability measure on G. And then there is one implication, is that if the Avez entropy is positive, then, so the Avez entropy is something you obtain by taking the convolutions of this probability measure, which gets the entropy of the convolution powers of this finitary probability measure. Then this implies that the number k minus infinity of a generator of the group is positive. There are a number of further results on this number k minus infinity of generators of groups in the regular representation. So I take a discrete group and the regular representation. For generators of Gromov hyperbolic groups, and there are connections with certain topological entropy of subshifts in some beautiful papers of Rui Okayasu. I will give you one of the simplest results, but because it completes the picture, I told you what happens with creation operators on the full Fock space. Now, one of the corollaries of the work of Okayasu is that if you have a free group of n generators, then he has the precise formula for the k minus infinity of the shifts by the generators. It's a logarithm of 2n minus 1. So now let's take a look at what happens in general with a situation of a group G and a finite generator K. So I'm having a discrete group G, which is finitely generated. Then, and a normed ideal K iota, and I'm looking at lambda, the left regular representation of the group G in little L2 of G. Then the K iota of lambda of K can have three possibilities. Either it's 0, or it's finite, or it's plus infinity. If I take these rough pictures, that is, I'm not looking at what the exact number is, I'm looking only 0, finite, or plus infinity, then this does not depend on the choice of the generator. I can change the generator, and the result is still 0, infinity, or 0, finite, I mean finite and positive, or infinity. And in the case of a group, what is nice is that this number, to compute it, one doesn't need to look at all the increasing sequences of finite rank positive contraction. It is enough to look at the sequences of contractions which are multiplication operators. So I'm in the group, I'm taking multiplication operators in little L2 of G, yeah? So this is functions on the group, yeah? And they are which grow to 1, positive, between 0 and 1, positive. So these are, if you want, multiplication operator or operators which are diagonal in the canonical basis of L2 of G, and compute this. So this becomes now function theoretic when you go over to groups. And what I can tell you, in case I'm looking at Kp, not at K minus P or the other one, Kp of the generator to be positive is actually the same thing as a notion in group theory. It's the Yamasaki P hyperbolicity. So Yamasaki P hyperbolicity is the same thing as Kp being positive. You can say, in a sense, that if you look at this K iota in Ki in the group case, it is kind of extension of what Yamasaki looked at with different norms. You have to look at the Lindenstrauss-Zafriri book, I believe, yeah? Gilles, yeah, and take all these symmetric norms, how they are called, and replace the P norm in Yamasaki's work with all these norms, and then you get all these K iota numbers. So here are a few examples what happens. From the things with Hermitian operators, if you take the group Zn, then the number K minus n of a generator is finite and non-zero. If you take the group G to be the discrete Heisenberg group, then the number, which is neither 0 nor infinity and is finite, it is n equal 4. It's a result of David Bernier, who was once my PhD student. And if P is infinity, there is something new to say. And it is due to recent results of Keller-Hals, Monod, and Roerdam. Using these, I could prove the following, that K minus infinity of the generator to be 0 implies that the group G is supramenable. Let me explain what this means. Supramenable is a notion due to Joseph Rosenblatt. It is a group G is supramenable if taking in G any set which is non-empty, there is an invariant finitely additive probability measure on the group, yeah, which on that set is 1, but where you allow it's only finitely additive, and you allow also the value plus infinity for certain set, which is G invariant, yeah? So that's the notion of supramenability due to Rosenblatt. For instance, groups with sub-exponential growth are supramenable. There are groups which are not supramenable but are amenable. Amenable implies amenable. And the Keller-Hals Monod Roerdam result is the following, that if G to be supramenable is equivalent to the following: there is no injection, no Lipschitz injection of a free group into G. Lipschitz with respect to this graph norm. And so it's kind of the dream of von Neumann, which proved wrong, that amenability is the same thing as a group not containing a free group. You have it here in a Lipschitz way and with supramenable. Supramenable is the same thing as not containing in a Lipschitz way a free group. That's a beautiful Keller-Hals Monod Roerdam result. Of course, since this number K minus infinity from perturbation point of view is so natural, it is also very natural to ask which are the groups for which the number k minus infinity is 0. And one may wonder whether it's not the same thing as being supramenable. So if we have also the other implication, not just that k minus infinity of the generator being 0 implies supramenable, but that also supramenable, the converse, implies k minus infinity being 0. There are other candidates for all this, and it is possible that all the candidates would fit together. Namely, it is not known whether supramenable is different from sub-exponential growth. So it is possible that sub-exponential growth be the same thing with supramenable, or sub-exponential growth being the same thing with k minus infinity of a generating being 0. All these are possible. And just yesterday I heard from Michael Rördam that Monod has a kind of intermediary notion between sub-exponential growth and supramenable. He doesn't know whether it's a different thing, but he has an intermediate notion, which of course may be also a candidate for being equivalent with this k minus infinity, lambda of k being equal to 0. Now about just a hint about about a recent direction where these things about perturbations of operators are going. You see, all these things about perturbation with operators were constructed using these numbers k iota of tau. So it's so many things done with just around some numbers. One would like to have more structure. And it has emerged that there is actually such a structure. And the structure is the commutant modulo a normed ideal. So what you do is you take an n-tuple tau, Tj, let's say it's Hermitian to simplify matters, and you take a norm ideal I with its norm I, and then you look at all the operators x, which commute with the elements of the n-tuple, modulo the ideal. So all the commutators are in I. And this is a Banach star algebra, which has a natural norm. It's a uniform norm plus the supremum of the norms of the commutators. And what is emerging is that the way to understand this Banach algebra is by looking at the analogy with the algebra of all operators on the Hilbert space and the compact ideal. So there is a compact ideal in this algebra, k, tau, and I. It's the intersection with the compact operators. And there is this kind of Kalkin algebra, the quotient of the Banach algebra, by the compact ideal. Yeah, so this is the important structure. There is the compact ideal in this commutant, and there is the Kalkin algebra. Now, what I can tell you about the case of the Macaev ideal is that the Kalkin algebra, if this number k minus infinity of the n-tuple tau is 0, the Kalkin algebra in this situation is always a C-star algebra. So though this is not a C-star algebra norm, but the Kalkin algebra, the quotient by the compact operators, is a C-star algebra. And if the number k minus infinity of tau is positive, then this Banach algebra, this Banach-Kalkin algebra, well, it's not a C-star algebra necessarily, but it is equivalent to a C-star algebra. That is, it is non-isometrically isomorphic to a C-star algebra. Of course, via simple algebra, all these are equivalent to C-star algebras in the usual Kalkin algebra of the Hilbert space. I want to add just a little thing to understand what the picture is. So you have here the ideal k tau of I. Here you have this type extension E tau of I, that's a commutant. And here you have the Kalkin algebra. This has many analogies with what happens in the case of the usual case of bounded operators on the Hilbert space. But it depends, of course, on conditions satisfied by the n-tuple, like the vanishing of this number k iota of tau. So for instance, the norm on this very often is completely determined by the norm on k, because this is a multiplier algebra. This is just the multipliers of the compact operators, very often. Another thing which happens often is that this E tau of I is the bidual of k tau of I. What you see for the usual compact operators, their bidual is all operators on Hilbert space. You have it also in this context. And then you have also, in many situations, but again with these numbers k tau of I vanishing, you have the kind of Grothendieck-Sakai situation that E tau of I has unique predual. So there can be also interesting things about the convex sets which appear here. Now, briefly, some references. There is a survey of mine in a volume edited by Picardello on harmonic analysis and discrete potential theory, which contains many of the older results. It's a good survey. Then there are some of, that's a paper having to do with entropy, which appeared in Ergodic Theory, a dynamical system in 1991. Then there are the recent papers with supramenability and questions about K-theory, which are on arXiv, and there are more papers like that with biduals, the unique preduals, all this stuff. There are computations of K-theory in certain cases for this type of Kalkin algebras, which show that they are not what you would think smooth algebras of the C-star algebras corresponding. Here is a Keller-Hals-Monod-Rördam paper on non-supramenable groups, which appeared in Documenta Mathematica 2013. The Rosenblatt paper in Transactions, which defines, I have here two of the Okayasu papers listed. Then there is a paper of Alain Cohn on the spectral characterization of manifolds, which uses very much this type of techniques. I developed this kind of perturbation theory techniques, and since it's a recent paper, it somehow made me think again about this kind of questions. And here you have also my paper with Guy David, where we looked at the non-integer dimension. That's what I had to say.
Thank you. So are there questions, remarks?
I have a question. Some of these quantities you define really look like Hausdorff dimension.
Bepan?
They look a lot like Hausdorff dimension.
Well, I mean, the results with Guy David give you something like a certain spectral measure having a kind of...
It's an uprising.
Yeah, it's a spectral measure we're talking about. That a spectral measure is some kind of absolutely continuous with respect to Hausdorff measure. Only Hausdorff measure is a very delicate concept. And what is with these numbers is that you go well beyond commuting n-tuples. It's a generalization of all these to non-commuting n-tuples.
Okay, more questions? So if not, so let's thank Dan again.